Projectiles Part 3, the launch angle needed to maximize the range. Again, not 45 degrees this time, but not because of air resistance like last time. It's because of height. Thank you, by the way, to C.E. Mungen. Fired from a height. Shot at this angle, at this speed, spending this time in the air, going this range, being fired from this height. Let's get to work. Equation for vertical displacement, initial height, landing at time t, going this far horizontally. This is t plugged back in. Speaking of plugging stuff in, our job is to find the theta that maximizes range. But first, we'll clean things up a bit with the double angle formula. Twice. Now, differentiate using the product rule. Well, not here. That's just a derivative. Not here either. See how r squared gives us 2r dr d theta? Now, u dv d theta, v du d theta. Okay, but where will r be a max when dr d theta is 0? Great, an expression for theta. Bad, it's in terms of r. And that's bad because we want to know theta so we can find r. Hey, look at that. Weird, but hey, you're the one who told us that tan 2 theta is r over h, so that's that, and this is the hypotenuse, cosine, and sine, and this is where it came from. So here we're taking a step back to go forwards, going towards an expression for r. This is how far the projectile will travel, which is not exactly what we wanted. We wanted theta. So plug that stuff in. Cosine, almost there. There. First, this ratio, v squared divided by hg. Think about it in terms of units. Okay, yes, the units work. Plug in this ratio and read out that angle. And when the ratio is large, big V, or small h, or very small g, then that means 45 degrees. Smaller ratios, and you're looking for a horizontal launch. But will it matter to us? Remember these guys? Does H matter here? Last time we were looking at air resistance for those projectiles. This time we are focusing on H, so it's a new ratio, and these are off the charts. Good thing we have an equation. R naught, again, is the distance that it would go in the simplest case scenario, no air resistance, H equals 0. And this is how far it would go when it was fired at 45 degrees and at the H mentioned. So the big question, can we get these projectiles to go farther if we lower the launch angle just a degree or two? And not really. And this might remind you of the results from part 2. Air resistance and launch height matter. Yes, they definitely matter. The angle needed to maximize the range does change. But the effect of that change, at least for these classroom launchers, is not huge. Wait a minute. The launcher on the left. What would happen if we included air resistance and launch height into the range calculation? Would they cancel out? Well, kinda, sorta. Again, that's the max range for a 5.5 meter per second projectile without air resistance launched at H equals 0. This is the range when the same projectile is launched 20 centimeters above the ground. This is the range when it's launched 20 centimeters above the ground and the angle is lowered slightly to 43.3 degrees, and that's the previous situation with the effect of air resistance plugged back in, included back in, with a VT of, 50 meters per second. So we'd need to find a new T up and a new T down and all that, which is about the same as that. So in conclusion, fire away.